In this video, we're going to cover section 7.6 on unimolecular reactions, specifically the SN1 and E1 reactions. As you can see in this figure, we have an alkyl halide reacting with solvent. And so there's no other reagents used in this particular reaction. The only reagent is the solvent in which this alkyl halide is dissolved. What we observe when we carry out this reaction is we end up with a mixture of products. We end up with a substitution product and an elimination product. And so as you can see in the figure below, the first step in the mechanism that leads to these two products is the loss of a leaving group. So you can see that we have the loss of this bromine atom as a bromide. As a result of that loss of the leaving group, we end up with an intermediate, and this intermediate is a tertiary carbocation. It's from this tertiary carbocation that we can either end up with a substitution product or an elimination product. The substitution product that results from this further reactivity from the intermediate, this is referred to as the SN1 reaction, whereas the path from starting alkyl halide to the elimination product is the E1 reaction. So that's what we're going to discuss today. Now the reason why, before we move any further, the reason why this is referred to as a unimolecular reaction is that the most important step in this reaction mechanism is the loss of the leaving group. And at this point in the reaction, only a single molecule is involved, the starting material, the reactant itself. So in the most important step, or what we often refer to as the rate determining step of this reaction, there's only a single species, a single molecule involved in the formation of this carbocation. So that's why we refer to these reactions as unimolecular. Now, as we've seen previously, we have an acronym associated with these reactions. S still stands for substitution and nucleophilic, and we've discussed the unimolecular aspect of this reaction. So here's the mechanism. It involves two key steps: loss of a leaving group and nucleophilic attack. So very much like the SN2 reaction, the same two arrow pushing patterns are found in this particular mechanism, but the order is different. As you can see, with the alkyl halide, your starting reactant, the first step is the loss of a leaving group to give you the carbocation intermediate. And once that carbocation intermediate is formed, then nucleophilic attack will occur. So nucleophilic attack will lead to your final product. Let's look at a more specific example of the SN1 reaction. So again, starting with a tertiary alkyl halide. So we have this tertiary butyl bromide. First step in the mechanism is the formation of the carbocation. If we look to the energy diagram below, we notice that the energy, the activation energy required for this step is quite large. Once we surmount this particular energy barrier and end up with our carbocation intermediate at this minimum, we see that the barriers after that, following that first step, are relatively small. It's because of this high activation energy barrier that we refer to this step as the rate determining step, meaning that the rate of the reaction is really dependent upon, to a large extent, on the kinetics of this particular step. So once we overcome this particular barrier, everything is somewhat downhill from there. So the rate of the reaction is very much dependent upon that particular activation energy. And that's described below in that particular statement. Now, once we have formed our carbocation, the next step is nucleophilic attack. And in this reaction, where solvent is your nucleophile, we see that it's the lone pair on the oxygen atom that is undergoing nucleophilic attack onto the carbocation. Now, we've said previously that alcohols like ethanol, methanol, and molecules such as water, these are poor nucleophiles. But again, we don't have any other option if that is the only species present in this system. So if it's just the alkyl halide dissolved in a solvent like ethanol, regardless of how poor it is, we also have a very good electrophile in that of the carbocation. So the reaction will occur even though the reaction may be relatively slow compared to systems where nucleophiles are stronger and alkyl halides are less encumbered. So what we see here is we have a neutral nucleophile. When a neutral nucleophile undergoes nucleophilic attack onto a carbocation, some part of that new entity, this new species, has to carry that formal charge of +1. And so although this electron pair now forming a new oxygen-carbon bond satisfies the formal charge of the carbon center to neutrality, 0, the oxygen now has, in some sense, overexerted itself in terms of its valence electrons. So it now has 3 bonds to its nearest neighbors and a single lone pair. So in that scenario, we know oxygen will take on a formal charge of +1. So again, it's really important to follow the charge to ensure that we're not losing or misrepresenting our structures. We need to ensure that the formal charge is represented as we go through our mechanism. Now, how do we get around that? Well, this will not be our final product. These charged species are still relatively unstable. And so you can see that the next step in the reaction is a proton transfer step. And that proton transfer occurs when another ethanol molecule of ethanol, will accept this proton. And in doing so, this bonding pair of electrons becomes the second lone pair on oxygen. So our substitution product is an ether. So in this example, the functional group transformation that we're showing you is the alkyl halide undergoing a transformation to a ether via the SN1 mechanism. Here's a cartoon to describe that particular process. Not completely accurate in the mechanism, but still a little bit funny. Now the E1 reaction is also a unimolecular reaction, but is the elimination pathway. So the pathway to the formation of an alkene. You can see that the first step in this reaction is identical to the first step in the SN1 reaction. We have the loss of a leaving group to give us a carbocation intermediate. The second step is different than the SN1 reaction, where we saw a nucleophilic attack. The second step in an E1 mechanism is the proton transfer. And you'll recall that there was a proton transfer also involved in the E2 mechanism. So the species that's involved in removing this hydrogen atom as a proton, accepting this proton, will be a base. Now, for our last example where ethanol was our only species in our reaction mixture, yes, ethanol is a weak base, but again, if nothing else is present in the reaction mixture, it will take on that role. Nonetheless, in the E1 reaction, either water or an alcohol will act as a base, deprotonating one of the hydrogens from a beta carbon on your carbocation intermediate and forming a new pi bond between the alpha and beta carbon. And so the net result is the formation of an alkene, and as side products, if you will, but as a part of the mixture, you'll have a protonated base, and we lost the leaving group in that first step. Here's an example of that same reaction that we saw earlier, where we have tertiary butyl bromide in the presence of only solvent, ethanol in this example. And you can see that ethanol is being used to deprotonate the carbocation intermediate. What's not shown and should be shown in this particular mechanism is that we form a protonated alcohol. So that becomes one of the species that's present in your reaction mixture after the elimination product is formed, or as it is formed. Now what's shown below is the energy diagram for these two pathways, both the SN1 and E1 pathway. And what we see, or what we observe experimentally, is that the SN1 product is more stable than the E1 product. So because the stability of the SN1 product, which is the carbocation that undergoes nucleophilic attack, or that is attacked by the nucleophile, because of this, when in our product ratio or product distribution, we will always form more of the SN1 product over the E1 product at normal, let's say, ambient or room temperatures. We'll talk about how we can increase that product distribution to favor the E1 product if we run this reaction at higher temperature. And we'll comment on that shortly. And as you can see, the pathways for both substitution and elimination are identical up until the formation of the carbocation. It's at that point where we have slight differences in the energy barriers and differences in the relative energy of the final products. So both from a kinetic standpoint and a thermodynamic standpoint, the SN1 product will be favored. Now the SN1 and E1 reactions, they both begin with the loss of a leaving group to form a carbocation intermediate. And then after that point, with substitution, you have nucleophilic attack, but with elimination, you have a proton transfer. Now it's possible for additional steps to be involved in the SN1 and E1 reaction mechanisms. And that depends on a couple things. It could depend on the nature of the starting material, the starting substrate. It could also depend on the nature of the nucleophile. Or it may depend on the nature of the carbocation that's initially formed. So there could be additional proton transfer steps. There could be a carbocation rearrangement. And so we're going to look at a few examples where this will occur. So in this example, we're starting with a tertiary butyl alcohol, T-butanol. And T-butanol, as shown, if this bond were to break, the leaving group would be the hydroxide ion. And you may recall previously that strong bases are poor leaving groups. And so we wouldn't expect this carbon-oxygen bond to break. Now, the only way in which this carbon-oxygen bond will break to form a carbocation intermediate is if we protonate the alcohol. So how do we do that? Well, we're going to add some acid to our reaction, to our tertiary butanol. And you can see that hydrogen chloride, HCl, hydrochloric acid, is being used as the source of protons. And so when HCl is present, this very weak acid will react with the stronger acid to give you the oxonium. So the oxonium now presents a different scenario. Now the leaving group would be a molecule of water. And so a water molecule is a much better leaving group than the hydroxide because A, it's a neutral species and a much weaker base. So once we form the oxonium, now we can form, through the loss of a leaving group, our carbocation intermediate. So just to recap, we have a proton transfer reaction occurring prior to the loss of the leaving group. And that's required because this is a poor leaving group and this is a much better leaving group. In reacting with HCl, we also generate the chloride ion, and that chloride ion will act as a nucleophile in our last step. So we form our carbocation intermediate through the loss of a water molecule. The chloride ion is our nucleophilic species, and so it will undergo nucleophilic attack onto the carbocation to form a tertiary butyl chloride. And so the main point of this particular slide is to show you that although this is the SN1 mechanism that we saw previously, we need to protonate the alcohol first so that we have a sufficiently good leaving group for carbocation formation to occur. Now, as I mentioned in the opening part of the last slide, it's possible that upon the loss of the leaving group from this alkyl halide, as shown, that we may end up with the potential for a carbocation rearrangement. And that's what's being shown in this example, that we have a alkyl bromide, or a bromoalkane. Upon the loss of the leaving group, loss of the bromide ion, we form a secondary carbocation. So there's two groups attached to that carbon center and a single hydrogen. So we form a carbocation. It's at this point that we will have a carbocation rearrangement. Specifically, we have a 1,2 methanide shift. So that methanide shift will result in the formation of a much more stable carbocation, the tertiary carbocation. And again, this is something to always look for when your intermediate is a tertiary, when your intermediate is a secondary carbocation. Secondary carbocations, stable as they may be relative to the primary methyl systems, they still prefer to undergo the rearrangement to the tertiary system if possible. And so you want to look to your neighboring atomic centers to see if there are any hydrogens or methyl groups that may undergo migration to that carbocation to form a more stable tertiary carbocation. So once the carbocation is formed, then we'll see nucleophilic attack, in this case from the chloride, and ACl is added in significant amounts, that it will be present in solution in a higher concentration than the bromide, the leaving group. So here we're converting a bromoalkane to a chloroalkane using sodium chloride. Effectively, the chloride ion as our nucleophilic species. Again, remember, NaJ is my reminder that anything next to sodium is going to give you the counter ion and J minus. So in this example, we have the chloride being our nucleophilic species. So the last example is very similar to the opening example that we looked at for SN1, where a proton transfer may be necessary after the two core steps of the loss of a leaving group and nucleophilic attack. And that's because the nucleophile that's used is a neutral species. And this is very common for SN1 reactions, where water and alcohols like methanol and ethanol are the most typical nucleophiles used in the SN1 reaction. And again, we refer to these reactions as solvolysis reactions because solvent is the only thing present that can act as a nucleophile and attack the carbocation species. So in this example, we have tertiary butyl chloride. It undergoes loss of a leaving group, loss of the chloride to give you a tertiary carbocation. This tertiary carbocation is quite stable, not undergoing or able to undergo any kind of rearrangement. And the only other species present in a reaction mixture is solvent. And so methanol will undergo a nucleophilic attack onto the carbocation to give us this oxonium species. This is not our final product. This charged species will further react with an additional alcohol molecule, methanol, through proton transfer step, to give you your neutral ether. And it's important to remember that in these solvolysis reactions, we have a significant amount of solvent present. So when we take a millimolar or even molar amount of this particular compound and dissolve it into solvent, the concentration of solvent is on the order of 50 molar. So aqueous reactions, for example, water is typically present at a 54 molar concentration. And so when solvent is needed in a reaction mechanism, as in this example for both nucleophilic attack and proton transfer, it will be available. It is present in significant amounts relative to the original reactant. Now that leads us to a discussion on the role that solvent can play in terms of stabilizing our intermediate species. So what we observe experimentally is that SN1 and E1 reactions, these are favored in polar protic solvents. And it's because both the carbocation and the leaving group, in our last example, the halide, these are well solvated by these solvents during that ionization process. So that loss of a leaving group step, in a sense, we're taking a neutral species and we're generating two ions from that species. The halide, the leaving group, the chloride in our last example, as well as the carbocation intermediate. So these are two species, ionic species. They both have formal charges greater or less than 0. And so solvents such as water and the alcohols, which again have that hydrogen bond donating capability, these are able to stabilize those particular ionic species quite well. And so what we typically observe in terms of the rate of a reaction, how quickly a reaction is going to occur, in the presence of water, this particular example, which we just looked at, that first step in the mechanism, the loss of leaving group, it's 40 times greater in the presence of water than it is in the presence of ethanol. But more importantly, or more dramatic, is that it's significantly higher than the rate of a reaction in a aprotic solvent like ether or diethyl ether. And so the use of water and alcohols like methanol and ethanol will significantly increase the rate of your reaction for an SN1 and E1 reaction specifically. And this can be looked at using energy diagrams as well, that polar protic solvents, they're able to stabilize the carbocation intermediates and the transition state in an SN1 reaction quite well. And that can be seen with the energy diagram, that a polar protic solvent lowers the energy of the transition state going from reactant to intermediate as well as intermediate to product. So solvent does play a role in both substitution mechanisms, but they have opposite effects, that you prefer a polar protic solvent. You want the hydrogen bonding donor ability of water and the alcohols for an SN1 reaction, because that helps to stabilize the carbocation and leaving group anions that are formed. Whereas for SN2, we don't want that same stabilization of the incoming nucleophile. We want the nucleophile to be free to react with the substrate. So if you have any questions about SN1 or the E1 reaction, send me an email so that we can set up an appointment on Zoom or start a discussion in our forum. Thank you.